Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course on general organic chemistry, and I hope you are enjoying this course with me and learning a lot. So this is general organic chemistry part 2 that we are doing. In part 1, you all know that we have discussed the nomenclature of organic compounds in 17 lectures. That is a very detailed discussion on nomenclature so that you have a thorough understanding of each and every concept of nomenclature. Now in this part 2, we are discussing about isomerism. In lecture number 1, we discussed about what is isomerism, what is the classification of isomerism, then broadly classifying it into two types, structural and geometrical isomerism. We started with a detailed discussion on structural isomerism. There we discussed in lecture number 1 two types. One was chain isomerism and the other was position isomerism, right? So I hope that is clear. Lecture number 2, what did we discuss? We discussed about three more types of structural isomerism: functional isomerism, metamerism, and ring chain isomerism. I hope again that is clear to you people. This is very important that you have a thorough understanding of each and every concept. In case there is any doubt, please feel free, put your doubts in the comment section. We will be glad to help you all. If you cannot put that, you cannot type that into the comment section. We have already given the email ID of ours at the end of every lecture. So you can just note down the email ID, put your doubts and send an email to us. We will be definitely reverting back to you within 24 to 48 hours for sure. Alright. So please do clarify your doubts. That is what I can say. That is going to be the best way you can prepare your concepts. Now in lecture number 3, what did we discuss? That was the last lecture. We discussed about a concept called as double bond equivalent, which helps us understand what are the various functional groups that can be present for a particular molecular formula, and this helps us draw all the possible structural isomers for a compound. Right, now we are going to continue the discussion further. We are just left with one type of structural isomerism, and that is tautomerism. So tautomerism, this is a very important concept. All right, this is a concept that you're going to use quite a lot. So this requires a detailed understanding. This is very important from your competition point of view also, because many questions they do come from tautomerism. So we will be discussing this in detail, and detail means that I will be putting 2 lectures for tautomerism. Why 2 lectures now? As I've already told you that this is a very important concept, so this has to be discussed in detail. In lecture number 1, in this lecture that is, what we will be discussing is what is tautomerism, then how do we make different types of tautomers. Alright, and then the next lecture, this is going to be a very basic lecture on tautomerism, and in the next lecture we are going to have a very detailed discussion. In fact, that is a discussion that I have kept separately because that requires some level of higher learning. Higher learning, actually this is going to be GOC part 3, that we are going to discuss many important concepts related to organic chemistry. And once you have learnt those concepts, you will be able to understand tautomerism part 2 a bit better. I will try my level best to come up to a level that you can understand quite a lot of tautomerism part 2 also. But the best would be that if you watch tautomerism 1 now, understand it completely. That is not going to be difficult at all. And then tautomerism 2 you should watch now, but then after we have completed GOC part 3. Okay, so this is GOC part 1, part 2 and part 3 that I'm going to put up this detailed course on general organic chemistry. Why such a detailed course? Because once you are through with your general organic chemistry in a very detailed manner, you will not find any difficulty in understanding organic chemistry. Organic chemistry is a very beautiful subject, very nice, very interesting, very scoring once you know each and every concept. If you just try to remember the reactions, you are going to fail. But if you understand each and every concept, I am guaranteeing you, you are going to excel in organic chemistry, and it is actually very interesting once we know everything. That is why we are going to put a lot of focus on understanding the concepts in general organic chemistry. Once you're through with that, perfectly fine. You're going to do really very well in your organic chemistry. I can assure you for that. All right. So As I was telling you, tautomerism part 1, you will be able to do that very well. You will understand everything. But in tautomerism part 2, there are going to be certain things that you will not be able to understand. Okay. But I will try my level best to give you very simple answers to those questions. And then my suggestion would be that once we have completed GOC part 3, just watch tautomerism part 2 once again. If you do that, your concept is going to become perfect. Alright, so let us begin the learning of tautomerism. What is tautomerism? Now, tautomerism is something, if you all remember in lecture number 3, when we were talking about the double bond equivalent, I told you that we will be drawing the structural isomers for C3H6O. I hope you all remember. In case you do not, and if you've not watched that lecture, well, you can go back and watch that lecture and you will understand what I'm connecting to. So there we had drawn the structural isomers for C3H6O, and there I told you one of the structures was propanol, the other structure was propanone, and then I had drawn two structures which I told you that one is a tautomer of propanol and one is a tautomer of propanone. So those structures, what are tautomers, is what I told you that we will be discussing in the next lecture. So I will be starting my discussion from there only. I will be drawing the structural isomers for C3H6O, and then we will be moving in with the discussion of what is tautomerism. Alright, so let us begin. So the first structural isomer for C3H6O in the last lecture, what we had drawn was propionaldehyde or propanol. The dB value, this had come as 1. There had to be a double bond or a ring structure to be present, and there was an oxygen present. So a double bond and oxygen, the first thing that came into our mind was a carbonyl group, and we drew a aldehyde, and then we drew a ketone. So these were the first two isomers which we could think about. Now after that we had to make more isomers. So what did we do? Then what we thought was, then why not make the bond between carbon and oxygen to be a single bond and the double bond between the two carbons. So what we did? Well, we made this oxygen attached to a hydrogen. Okay, this is a OH group. Now the functional group has changed, and now we have the double bond between the two carbons. So the dB value remains the same, the molecular formula remains the same. So these two, they are structural isomers of each other. Okay, you can see that the functional group is aldehyde group. Here we have a OH group, so this is an alcohol. So they are functional isomers, but what I told you was that these are very special type of functional isomers. These are called as tautomers. Similarly, if you look at acetone, the next structure that we drew from here was that instead of this double bonded oxygen, we put up a OH group here, just like instead of this double bonded O, we had put an OH group, and the double bond is shifted between two carbons. So now this is propene 2-ol, and I also told you that this is a tautomer of acetone. So now what we are going to learn is what are these tautomers, what is the phenomenon of tautomerism. That is going to be this whole lecture. So let us understand step by step in detail what is tautomerism. So first of all, obviously the definition of tautomerism. So tautomerism, this is also called as desmotropism. It is also called as dynamic isomerism. It is also called as cryptomerism. It is also called as keto-enol tautomerism. But that is going to be just one part of the whole tautomerism, keto-enol tautomerism. Alright. So now let us understand what is the definition of it. So here the same molecular formula, this is going to represent two compounds that exist in a dynamic equilibrium with one another. Alright, so the same molecular formula, as we have propionaldehyde and propene 1-ol, the molecular formula is the same, but the two compounds, they exist in a dynamic equilibrium with one another. Okay, what this means is that these two are going to be present in equilibrium with one another. It is going to be always a liquid phase, or it is going to be a gaseous phase, where you will be seeing these two isomers and they will be existing in equilibrium with one another. And it is a dynamic equilibrium. It is always a changing equilibrium. Sometimes it is going to be this and sometimes it is going to be this. Both are interconvertible. Alright. Now So you understand why it is called as dynamic isomerism. Generally, when we have functional isomers, the two functional isomers, they are independent structures that we have. They're not existing in equilibrium with one another. We are not interconverting them into one another spontaneously. That is not happening. But here this is because they are in dynamic equilibrium with another, they are present in a same reaction. This is a reversible reaction. So that is why we have defined it into a special type of isomerism, that is tautomerism. Now this is also called as desmotropism. So desmo means bond and tropism means turn. So this is called as bond turn. Why is it called as bond turn? Because the interconversion of the two forms, this involves a change in the bonds. What you can see is here we have a double bond between carbon and oxygen. Here we have a double bond between the two carbons. So there is a change in the bond positions, you can say, and that is why we call this as desmotropism. Alright, the three words, they are clear to you. So now let us move on to the types of tautomerism. So the two types of tautomerism, they are called as a dyad type or a dyad system and a triad type or a dyad system. What do we mean by a dyad? Well, dyad is going to refer to 2 and a triad is going to refer to 3. What is 2 and what is 3? Dyad refers to 2 polyvalent atoms and a triad, this refers to 3 polyvalent atoms. Okay, so 2 polyvalent atoms and 3 polyvalent atoms. You will just now get this in writing also. Okay, first of all, let us discuss the dyad system. First, I will be showing you and explaining with the help of an example, and then we will be putting it in words. Okay, so the example we have is of HCN. Alright, so HCN, this is in equilibrium with hydrogen isocyanide, that is HNC. So you can see over here that both of these two, they have the same molecular formula. Alright, and the functional group, this is different. So this is a functional isomerism also, but this is a special type of functional isomerism because these two, they are in equilibrium with one another. Alright, so that is why we call it as tautomerism. Now in this tautomerism, what you can see is that we have two polyvalent atoms. This is polyvalent atom number 1. This is polyvalent atom number 2. What is polyvalent? Having more than one valency. Alright. So in this was my atom number 2. This is my atom number 1. So what you can see is that here the hydrogen, this was attached to carbon, and here the hydrogen, this is attached to nitrogen. So the hydrogen, this has shifted from atom number 1 to atom number 2 during the formation of the tautomer. Alright. So I hope you understand what have we done. We have shifted the hydrogen from position number 1 to 2. So a dyad system, this involves 1-2 migration of a proton or hydrogen from one polyvalent atom to the other within the same molecule with necessary rearrangement of bonds. So the hydrogen has shifted its position from one polyvalent atom to another. And because there are two atoms involved, so we call this as a dyad system. So next we have a triad system. So here we will be having 3 polyvalent atoms and a shifting of position of hydrogen from where? From position number 1 to position number 3. Let me show you that. Alright. So we have, let us say, 3 atoms A, B and C. This is my atom number 1. This is my atom number 2. This is my atom number 3. Alright. This is my atom number 1. This is my atom number 2. This is my atom number 3. Fine. So what you can see is here the hydrogen, this is attached to atom number A, here 1, sorry, and here it is attached to atom number 3. So the hydrogen, this is shifted from position number 1 to position number 3. So such a system we call as a triad system. Involves 1-3 migration of proton from one polyvalent atom to the other within the same molecule with necessary rearrangement of bonds. Perfectly fine. Now, what is this A, B and C? Just remember this as well. B, this can be any atom because you are going to see many types of triad systems. So you have to identify whether in this system there is tautomerism happening or not. Alright. So how you will identify? We have atom B, which can be any atom. it can be anything. Okay, so you will be seeing the examples also. Then we have atom A. This atom A, you just now see, this is at position number 1. What does this have? This can also be any atom, but it has to have a hydrogen attached to it. Hydrogen should be attached to it. If it does not have a hydrogen, it is not going to exhibit tautomerism. Just remember this. Okay, but this should not be itself hydrogen. Okay, it has a hydrogen attached to it. It is not itself a hydrogen. Fine. And see, this is a polyvalent atom again, and this can be a nitrogen, it can be a oxygen, it can be a sulfur. In this case, you can see, well, sorry, not in this case, I'll just show you the example also. So what we have, the triad system, there are going to be many triad system, and the most common triad system, this is the keto-enol tautomerism. Okay, so why we have keto-enol? First of all, just understand the meaning, then I'll show you how this is a triad system. Okay, so keto, this refers to the carbonyl group. It can be an aldehyde, it can be a a ketone, but in both of them they contain the carbonyl group, so we will be calling it as a keto. And enol, en means a double bond and all means a OH. So we will be having a C double bond, and this carbon which is forming a double bond, this will also be having a OH group. Then we will be seeing that the two functional isomers, they are present and they are going to be in dynamic equilibrium with each other. So we will be calling that as a keto-enol tautomers. Alright, let us see an example first of all. So here first of all, this is a triad system. Let us identify this. Okay, so I am putting this carbon which is forming a double bond as carbon number 2, right? And this is my carbon number 3, my atom number 3, and this is my atom number 1. So you can see 3 polyvalent atoms, atom number 1, atom number 2 and atom number 3. Atom number 2, this could be any, and atom number 1, this had to contain attached to a hydrogen. So you can see there are 3 hydrogens attached in this acetaldehyde, and atom number 3, this had to be a carbon, this had to be a oxygen, or it had to be a sulfur. Fits in into my position, everything is fine. Alright, so now what we are going to do, we are going to shift a position of hydrogen from position number 1 to position number 3. When we do that, what will happen? One hydrogen less here, it is a CH2. Hydrogen has shifted to position number 3, so instead of a O, now we have a OH, and the double bond, now we have to satisfy the valencies. So from in between 2 and 3, this has shifted to position number 1 and 2, right? So these two, they are called as tautomers. I hope this is clear how we have shifted the position of hydrogen from 1 to 3, and then the double bond, this has shifted this position from in between 2 to 3 to 1 and 2. This is what we call as tautomerism. I hope this is clear. Now why do we call it as a keto-enol? Here we had a carbonyl group, here we have a double bonded OH group. Okay, so the 2 carbons, they are having a double bond, and one of the 2 carbons, this is also having a OH. So this is what we refer to as a keto-enol tautomerism. Now the next thing what you can see is that here it is written 100% and here it is written in all forms 0%. What this means is that whenever we have a 2 compounds in equilibrium with one another, the equilibrium can be shifted to any side. You all know that, right? So if the equilibrium is more towards the reactant side, this means that the product is not going to be found. But if it is shifted more towards the product side, you will be seeing that the whole of the reactant, this has been consumed. So what this keto form 100% means is that we have only the reactant present and the product is not present. Why is it not present now? It is not present because this is highly stable, this is not stable. Okay, in comparison both of the two, we will be seeing that this is highly stable than the other, and therefore what we will be seeing is that the reaction does not proceed to completion. We will be having only the reactant, so this is going to be nearly 100%, almost 100%, and we will not be seeing the vinyl alcohol being formed in this equilibrium. Okay, I hope this is clear. We will be talking more about this in the next lecture. Okay, the percentage, why this is being formed, why this is not being formed, this is something that I will be putting a complete video in the next lecture so that you have a thorough understanding. Here, let us just try to identify which of the compounds this is forming a tautomer, which is not forming a tautomer. This is what we will learn in this lecture. We will learn what is a possible tautomer of one structure that is given to us. So the next example that you can see is a acetone and propene 1, propene 2 all right. So this is what you have seen previously also while we were discussing the isomers of C3H6O also. So here what you can see is, let's now again number the carbons. All right, the carbon present in the center, this is my carbon number 2. Fine, this is my carbon number 1, and this is my atom number 3, sorry. Okay, so atom number 1, which has hydrogens attached to it. Atom number 2, it can be any atom, and atom number 3, this is an oxygen, a nitrogen, or a sulfur. So my structure is finished, right? So perfectly fine, no problems. Now the hydrogen, this is going to shift from position number 1 to position number 3. When it does that, this will be a CH2, and here we will be having a OH. The double bond will also position changing, right? So this is 1 and 2, and here it was initially 2 and 3. So again the same thing, this is happening. You can identify what has happened. The hydrogen, this has shifted its position from 1 to 3, and the double bond, it has shifted its position from 2 to 3 to between 1 and 2. So you can say that it has shifted its position from 2 to 1. All right. So again, now you can see in this the keto form, this is 99.7%, and the enolic form, this is almost 0%. Again, this means that the keto form, this is more stable than the enol form. In generally, the keto-enol tautomerism, what you will be seeing is that the keto form, this will be more stable than the enol form, but there will be some exceptions where you will be seeing that the enol form, this is going to be more stable than the keto form. Again, all this we will be discussing in the next lecture. Now, before we move on further, just one thing, do remember that HCN at HNC, that is hydrogen cyanide and hydrogen isocyanide, they are tautomers of each other. But if we talk about the alkyl derivatives of it, we will be having a RCN and a RNC. Here what you will be seeing is that they are not going to be tautomers of each other. They will be simply functional isomers. They will not be existing in an equilibrium with one another. They are going to be an independent series that we will be forming. Alright. So the alkyl derivatives of hydrogen cyanide and the alkyl derivatives of hydrogen isocyanide, they are functional isomers. They are not going to be tautomers. Just remember this. Okay. So let us see one more example now. We have cyclohexanone. Can we number the atoms over here? So this is going to be my atom number 2, this carbon. This is my atom number 3. Okay, this has to be an oxygen, a nitrogen, or a sulfur. And this is going to be my carbon number 1. This can be this also, this can be this also. Okay, so here what you can see is this carbon over here, which is atom number 2. This is forming 4 bonds, so there is no hydrogen over here, and these two, they will be having 2 hydrogens. So it can be this and it can be this and, well, later on examples you will be also seeing that there you can remove a hydrogen also. There are going to be many examples, so you will be understanding. Okay, so my atom number 1, this should have a hydrogen attached to it, and you can see that both sides the hydrogen is attached, so you can remove a hydrogen from any of these 2 carbons. Okay, so we are shifting this supposedly, and this is going to be a 1,3 shift, so this is going to shift to this position. What are we going to get? Well, we are going to get another isomer of this, which we call as a tautomer. So can you see over here, from position number 1 to position number 3, the hydrogen has shifted, and the double bond, this has shifted from between 2 and 3 to now between 1 and 2. So this is cyclohex, 1 in 1 all. So this is a keto and this is a enol. A keto-enol tautomerism. Again, what you can see over here is 98% is cyclohexanone and 1.2% is enol. All right. So what do we understand is that in all these examples, what you have seen is that the keto form of all the monocarbonyl groups, there was only one carbonyl group present in these structures. This was more stable than the enol form. This was more stable than the enol form. So why is this more stable than the enol form? This is more stable because the carbon bonded to oxygen by a double bond, this is of a greater strength as compared to a carbon-carbon double bond. Okay, so this is more stable. So we will be requiring more energy to break it. The bond dissociation energy for the carbon oxygen double bond, this is 364 kilojoule per mole, whereas to carbon carbon double bond, this is 254 kilojoule per mole. So we require more energy to break this bond in comparison to a carbon carbon double bond, and hence the structure, this is more stable than this, right? So this will not be breaking and getting converted into this structure. So what we see is that we have more of this at the equilibrium point. Perfectly fine. I hope this is clear. All right. But do not worry. We will be talking in detail about this in the next lecture. Fine. Now, the next type of triad system where you can see a tautomerism of the same type, this is a nitro tautomerism. All right. So this is shown by primary and secondary nitro compounds having an alpha hydrogen, and tertiary nitroalkanes without any alpha hydrogen, they do not show tautomerism. So you can see over here what is the chief requirement. We have to have 3 polyvalent atoms. Now you can see this nitrogen. This can be any atom, I told you. So this can be my any atom. This is my atom number 3, this oxygen, and this is my atom number 1. So this carbon, this has to have hydrogen. If it has hydrogen, it is going to be either a primary or it is going to be a secondary. If it is going to be a tertiary, well, this is going to be substituted, so it will not have any hydrogen. So essential condition is that this atom number 1, this should contain hydrogens. Perfectly fine. Now the next, this can be any atom, and the atom number 3, this is a double bonded oxygen, nitrogen or sulfur. So again, my satisfying condition for tautomerism I can see in nitroethane. This is the nitro form, and if I draw the tautomer of it, what is going to happen? I am going to shift a hydrogen from position number 1 to position number 3. So let us do that. So this is going to be a reversible condition. So what you can see now is that we have shifted the hydrogen from position number 1 to 3. This was a CH2, now this is a CH. This was a O, this is now a OH. So the position of hydrogen from here to here, and the double bond, this has shifted its position from this to between the carbon and nitrogen now. Perfectly fine. This is called as the SC form. This is the acidic type. Actually, this is an acid. So this we call as the AC nitro. This is a nitro form. This is a AC nitro. This is isonitromethane. I hope this is also clear now. So let us see some more examples of a triad system of tautomerism. So the next triad system is nitroso-oximino system, and the name sounds to be a bit difficult, but do not worry. You have to study a lot of organic chemistry. So by the end of class 12, you are going to know all these. What do all these mean? For now, just let us concentrate that we are given some structures and we have to identify whether they are tautomers or not. So the example we are taking is of nitroso-ethane and ethanol oxime. The structures now they are in front of you. So this is nitroso ethane, where we have a carbon bonded to a nitrogen with an oxygen double bond. All right. So, and in the oxime, what we have is a carbon double bonded to a NOH, nitrogen with a OH group. So this is what we have as an oxime. Now, how are we going to identify whether they are tautomers or not? So the first condition was that we should have a nitrogen or oxygen or a sulfur which is forming a double bond with an atom, right? So this is my atom number 2, This is my atom number 3 and this is my atom number 1, and my atom number 1, this should have a alpha hydrogen. So this is my alpha carbon and these are the 2 hydrogens which yes it can replace. So the hydrogen from position number 1 is going to shift to position number 3. The double bond is going to shift from here to this position. The structure that you will be getting is that of ethanol oxide. I hope you can now identify everything. So CH3 instead of a CH2, now we have a CH. One hydrogen has shifted to the oxygen, so this has become OH, and the double bond, this has shifted to between nitrogen and carbon now. Now here the next system. So this is imine-amine system. Here the example that I will be taking is propane 1-imine and prop 1-ene 1-amine, which are going to be the tautomers. So let us again identify. Do not worry about the naming system. We can do that later on. All right. But well, this I can show you also. So this is a NH2 group. So this is amine. This is attached to carbon number 1. So this is 1-amine. The double bond is present between the 2 carbons. So it is going to be carbon number 1 having a double bond. So it is 1-ene. There are 3 carbons. So it is propan. So propan 1-ene 1-amine. So this is ene-amine form. This is imine where we have a carbon double bonded to a NH. Fine. So I hope now you can understand also slightly, but you will be learning about this nomenclature. Do not worry later on. So now we are going to identify whether they are tautomers or not. Again, what we need is a atom number 3, where we can see now it is a nitrogen, a oxygen or a sulfur, which has to be having a double bond. Yes, it is having a double bond, so this atom becomes 2. And my atom number 1, this is should be having an alpha hydrogen. Again I can see 2 hydrogens. So this propane 1-amine, this can form a tautomer, and it is going to be this hydrogen which is going to move from 1 position to 3 position. So again I can see my hydrogen being reduced from here, added up over here, and the double bond, this has shifted from this position to this position. So you can see a double bond here. Perfectly fine. So again the tautomers, they are visible to you. Very good. Now let us see another system. We have amido-imidol system or the thioamido-imithiol system. Now again the names, they are difficult. Do not worry, but it's okay. So what is this? CONH2. This is what? This is an amide group. This all of you know. This is the formula for urea. Alright. Now urea, again what you can see is that we have a carbon double bonded to oxygen. This is my atom number 3. This is my atom number 2, and this is my atom number 1. This can be also my atom number 1, either of the 2 nitrogens. These both of them, because they have alpha hydrogen, so we can remove a hydrogen from any one of them. So what we have done is we have removed a hydrogen from this place. All right, so this going to position number 3. So what you can see is the hydrogen has reduced, the O has a hydrogen now, and the double bond is between the nitrogen and the carbon instead of between carbon and oxygen. Again you can see what are the tautomers being formed. Very good. So this is called as the imidiol system. Next we have a thioimido and imithiol system, where instead of oxygen we will be having a sulfur. The rest the same, there is no difference. So we have a carbon bonded to sulfur. This is my 3, this is my 2, this is my 1. A hydrogen from here goes to sulfur. This forms SH. The double bond has shifted. Perfectly fine again. So I hope now you are all understanding what are the various tautomers being formed, how they are going to be formed. So next we have the characteristics of tautomerism. The first we have tautomerism or keto-enol. This arises due to the exchange of hydrogen atom between 2 polyvalent atoms present in the molecule. The change is accompanied by the necessary rearrangement of single and double bonds. So you all now know in a Dyad system the hydrogen is shifting a 1 to 2 position, whereas in a triad system it is shifting from a 1 to 3 position. So it is a shift of hydrogen atom, and it is also called as keto-enotropy because this is a shift of a cation. The next, the reversible intramolecular change. So I hope nothing to tell that it is happening inside the molecule, and this is a reversible change. The separation of tautomers, this is a bit difficult due to dynamic equilibrium between the two, but yet we can separate them by special methods. The tautomers, they differ in their stability, and the less stable form, this is called as the labile form. Again, we've already discussed that the keto and the enol form, for example, they are only one of the two is going to be more stable. Generally, it is the keto form that is stable. So the enol form, that will be called as the labile form. Wherever you will be seeing in the next lecture that the enol form is more stable, the keto form, this will be called as the labile form. The tautomers, they exhibit properties of keto as well as the enol form. So they are in dynamic equilibrium. What we see is that they are ever changing. So whenever a reaction is being done on this compound, what you see is that they exhibit properties of both the aldehyde or the ketone group as well as the unsaturated alcohol. Both of the reactions, they are going to be seen, and that is actually how tautomerism was discovered, because there were compounds that they were giving properties of both aldehydes, ketones as well as that of the unsaturated alcohols. So that is how the phenomenon was coined up also. Okay, so next we have that the tautomers, they are in dynamic equilibrium with each other and they are interconvertible. Again, we've discussed this. So two tautomers, they have different functional groups. One, for example, in the keto enol isomerism, we have a keto group and we have a unsaturated alcohol, and now we have seen so many examples: the cyanides, the isonides, cyanides, the nitro group, the SC nitro group. So many examples you've already seen. Both the tautomers will be having different functional groups. The tautomers, they have no effect on the bond length, so that is not going to change. And the next we have that they have no contribution to the stabilizing of the molecule. They does not lower the energy. Okay, there is going to be no effect of that sort to be seen. Tautomers, they may occur in planar as well as non-planar molecules. So the next we are going to do a very important discussion on tautomerism is not resonance. First of all, you should have an understanding why we are comparing the two. Well, when you're going to study your organic chemistry, you're going to see lot many examples of resonance. Okay, it is going to be that time that you're going to confuse many things. But I am discussing it over here because you're learning it and you will be remembering this better. Okay, now you have studied about resonance, not much about it, but you have studied about resonance in chemical bonding, where you studied that for a compound where there are going to be more than one structures possible, but none of the structure, this is going to explain entirely the properties of that compound. That is what we call as resonance. Fine. Similar to it, we have tautomerism also. For example, the most common form, I take the example of keto-enol tautomerism only. So we have a keto form, we have an enol form. We have more than one structures possible for a compound. If we take the keto form, it will not be able to explain why the compound this is giving the properties of an alcohol. If we take the enol form, we will not be able to explain why the compound this is giving the properties of an aldehyde or a ketone. You will be studying all these properties in detail. What are the properties? What are the chemical reactions that the aldehyde ketones they undergo? What are the properties that the alcohols will undergo? But none of the two structures this will be able to explain all the properties. So therefore, tautomerism, this seems similar to resonance. More than one structure possible, none of the two structures possibly explaining all the properties. But they both are different. Now why they are different, let us understand this. First of all, tautomerism, this is a real phenomenon. This is not hypothetical. Resonance is a hypothetical phenomenon. We constructed this phenomenon to explain the properties of a compound. Whereas tautomerism, this is a real phenomenon. How do we know this is a real phenomenon? Because the tautomers, we can isolate them. We can do that with a difficulty, but we can do that. But the resonating structures, they cannot be isolated. Okay. So tautomerism, this is a real phenomenon. Resonance, this is a hypothetical phenomenon. In tautomerism, there is the movement of atoms happening. Hydrogen is moving from one place to another, whereas in resonance, it involves the movement of electrons only. The functional groups, they get changed in tautomers. So we have different functional groups, whereas in resonance, the functional group that remains the same. It is the movement of electrons only. So there is going to be no change in the position of the atom. So there is no change in the position of the functional group. Next, we have that the tautomers, they have no contribution to the stabilizing of the molecule, and it does not lower the energy, whereas resonance, this is going to increase stability and the lowering of energy. So you will be understanding more of this when you're going to see some examples where the resonance is going to happen. But just remember that the tautomers, they are not going to contribute anything to the stability, no change in energy, whereas the resonance, this causes an increased stability and the lowering of energy. Another point you can add is that what we just now discussed, that the tautomerism, this is not going to cause any change in the bond length, the bond angle, the bond order. Whereas what we see in resonance, there is a change in bond length, bond order, etc. All right. So that is how tautomerism, this is different from resonance. This is not going to be resonance. So the next we have the essential conditions for tautomerism. Some things you have already understood and some things you are going to understand now because you are going to pay a lot of emphasis to it now. Alright, so the first condition is that the compound, this must have an electronegative atom like nitrogen, oxygen or sulfur bonded by a double or a triple bond. As you have seen in the various Dyad and Triad system, a carbon double bonded to oxygen, a triple bond with nitrogen, a nitrogen oxygen double bond, carbon with a double bonded nitrogen, again with a carbon and a sulfur. So all these you have seen in the various systems. So I hope I do not have to tell you that this is my atom number 3. Alright, so we have atom number 1, atom number 2 and atom number 3. Atom number 2 could be anything. But atom number 3, this had to be a nitrogen or oxygen and a sulfur. And what about atom number 1? The atom number 1 was the one which had to have a hydrogen attached to it. So the compound, this must have at least one acidic alpha hydrogen atom. Now what is this alpha hydrogen atom? So for example, when we are showing keto-enol tautomerism, let us see examples. We have acetophenone, we have butanone and we have propion aldehyde. So what are alpha hydrogens in them? You have this to be the functional group. The carbon next to it is called as the alpha carbon. Alright, and if that carbon has hydrogens attached to it, that will be called as the alpha hydrogen. So in acetophenone, what you can see is that this is the functional group. So the carbon next to it, this is a methyl group. So this has hydrogens. So these are going to be the alpha hydrogens. On the other side, we have a benzyl group. A benzyl group, this will not be having any hydrogen. I hope you can understand. We have C6H6. At every corner, there is one hydrogen. So there is a hydrogen here, there is a hydrogen here, a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. That is why it is C6H6. When I am making a bond of this carbon of the benzene ring with the carbonyl carbon, the hydrogen has gone from here. Now this portion is C6H5. This is the phenyl group. Alright, so C6H5, this is the phenyl group and it does not have hydrogen over here which is attached to the carbon. So this carbon here, this does not have any alpha hydrogen. So the alpha hydrogen is present only for the carbon of the methyl group. This is, I hope, clear to you people. Alright, so in acetophenone, we will be having alpha hydrogen. So if it is alpha hydrogen present, we can have a shift of this hydrogen from position number 1 to position number 3. So 1, 2 and 3, hydrogen at present at position number 1 will be going at position number 3 to form the corresponding enol form. Fine, perfectly clear. Now in butanone, what you can see, we have a alpha carbon, right? So carbon to this side of the functional group, this will be also alpha carbon. The carbon on the other side, this will also be the alpha carbon. Both of them, they are now alpha carbons and the hydrogens attached to them, they will be called as alpha hydrogen. Now when this structure, if you see, this is an unsymmetrical ketone. We have different alkyl groups attached on either side of the functional group. So it is going to form two types of enols. Okay, so let us draw that also. So what you will be seeing is this, okay. So the hydrogen gone from position number 1 to position number 3. Double bond at position number 1. So this is one type of enol that will be formed. And the other type of enol will be formed when the hydrogen will be removed from carbon number 3. So we have a CH3, a C, double bond CH, and the hydrogen bond to the oxygen to form the OH group. Alright, and the next is going to be CH3. So these are the two types of enols that can be formed from butane 2-on because this is an unsymmetrical ketone. I hope this is clear. Now, both of these two enols, they will be formed. One is going to be formed in a higher percentage than the other form. Now, which is going to be formed in a higher percentage and why it is going to be formed, this is again what we will be discussing in the next lecture. So the next lecture is going to be entirely on the understanding of what is going to be the stability of the compounds that are being formed, which is going to be formed in a higher and a lower percentage. Okay, so we have butane 2-on because this has alpha hydrogens. It has a double bonded oxygen, so this can show tautomerism. Next, we have propion aldehyde. So in this, is there any alpha hydrogen present? Yes, there is a alpha hydrogen present. So you can see the carbon next to the functional group. This is the alpha carbon. These are going to be the alpha hydrogens. So again, both the conditions, they are satisfied. So this compound, this will also be showing tautomerism. But now let us look at one exception also. The exception is that we have para benzoquinone which has alpha hydrogen, but because they are present on a double bond, they are not acidic and therefore it does not show tautomerism. So this is para benzoquinone. So here what you can see is this is my carbon number 2. Let me make that. Okay, so this is my carbon number 2. This is my my atom number 2 and atom number 3. All right, and this is my atom number 1, or my atom number 1 can be this. So my atom number 3, this is a oxygen. My condition satisfied. It should have a double bond or a triple bond. That condition is also satisfied. And my atom number 1, this should have a hydrogen, right? So my this condition is also satisfied, yet this compound, this does not show tautomerism. Why it does not show tautomerism? Because if you draw the tautomer for this, what you will be seeing is, okay, let me draw just of one side. This side, my carbon, this is my O, this will be the H, right? And the double bond will shift to this position. So this is what I will be getting. Right, so this is my structure. Now here what you can see is that these two double bonds, they have come together. Now when two double bonds, they are present consecutively together with each other, when this is going to be a very unstable compound, this will not happen. This compound will not exist because this is going to be highly unstable. That is why what we see is that para benzoquinone, although it has a alpha hydrogen, but we cannot remove that hydrogen. Being acidic means that we can remove that hydrogen easily. If we can remove a hydrogen easily, that compound is acidic. For example, you have HCl, you have H2SO4. So in HCl, you can remove a hydrogen easily. That is why it is called an acid. H2SO4, it can release two hydrogen ions. That is why we call that to be an acid. So similarly, when we can remove a hydrogen, we call that hydrogen to be an acidic hydrogen. Alright, so acidic alpha hydrogen, a hydrogen which can be removed very easily from the alpha position. So here also we have a hydrogen which is present at the alpha position, but this hydrogen we cannot remove. So this is not acidic and this is not going to show tautomerism. I hope you have got the concept very well now. So the alpha hydrogens, now you can see them labeled also. Now I have one question for you. This question is not one question. This has 10 parts. You have to tell which of the following compounds they are going to form tautomers. And you can do another thing also, that you are going to make the tautomers for this compound. I have not put that in the question, but you can make the tautomers also for these compounds. Alright. So let us do that. Pause the lecture, make the tautomers, and then we will be discussing them. So now if you have resumed the watching, so let us one by one see which of the compounds this is going to form a tautomer or not. So let us check the answers to the questions. first we had was acetaldehyde. So you have to tell that whether this is going to show tautomerism or not. And now I've added a question that if it can show tautomerism, draw the corresponding structure. All right. So for acetaldehyde, now how are you going to see whether this is going to do tautomerism or not? So you are going to identify 1, 2, and 3. So what I can see is that I have an oxygen. Yes, I have an oxygen. I have a double bond. Yes, I have a double bond. So this is going to be my atom number 3. This is going to be my atom number 2. And my atom number 1 is going to be that where I can see some hydrogens attached to it. So the CH3, this is going to be my atom number 1. All right. So I can identify that the double bonded oxygen is there and the alpha hydrogens are also present. So what am I going to do? Well, I'm going to shift one of the hydrogens from 1 position to 3 position, and this compound, this can show tautomerism, right? So the number of alpha hydrogen this structure has is 3, and this can show tautomerism. And the next, I have added the question, so we will be drawing the tautomer for this as well. All right, so this is going to be a CH2. One hydrogen has been removed. We have the next carbon, that is atom number 2, and we have atom number 3, the oxygen. And from position number 1, we have put the hydrogen at position number 3, right? And the double bond, this has to shift from this position to this, right? Perfectly fine. So we have done that. And the other side, the carbon had a hydrogen, so we have made this structure. So this is the tautomer for acetaldehyde, and we have already discussed while we were seeing the examples of keto-enol tautomerism also. Okay, now my next question, I'm not finishing it up over here. The questions, they can be asked to you that you have to identify a pair, whether they are going to be tautomers of each other or not, which you can easily identify by seeing 1, 2, 3 that the corresponding structure is a tautomer or not. The other is that you will be given 4 choices and you have to find which of the following is showing tautomerism or not. Now, in that question where you are given 4 structures and you have to tell whether those compounds, they will show tautomerism or not, you can be given this keto part of it. You can also be given the enol of this. Okay, and then you may get confused whether this structure is going to show tautomerism or not, because what you have studied is the keto part. This you will very easily identify, you will practice also and you will do, but this is something that will get confused. So what do? We are just going to slightly modify number 1, number 2 and number 3, and then you will be able to identify, even if we have a enol, how we are going to convert that into a keto, and also how, if you are given a enol, you are going to identify whether this is going to show tautomerism or not. Okay, so what do? We need an oxygen. This structure has an oxygen. We need a double bond. This structure has a double bond. All right, we need a carbon, we need any atom B, right? So this is my atom B, which should be bound to oxygen, and this also should be bound to another polyvalent. So the three atoms, they should be polyvalent, right? For keto, what did you study was that the double bond was either with a nitrogen or a oxygen or a sulfur. Now, if I change this and I tell you that for the enol part, if you have to check tautomerism, do one thing, just remember that it can be a carbon as well, which is forming a double bond. So it can be a carbon, it can be a oxygen, it can be a nitrogen, it can be a sulfur. Why I have written in this order is because this form cons. So you can easily remember this. Okay. So now you can see that we have a double bond. The double bond with a carbon, and yes, we can make a double bond with carbon. Okay, so this is now going to be my atom number 3, which is forming a double bond. Here also the atom 3 was forming a double bond. Here also the atom 3 is forming a double bond. Okay, now this is my atom number 2, with which the atom number 3 is forming a double bond, which has to be a carbon, an oxygen, a nitrogen or a sulfur. Fine. And now the next is my atom number 3. Now this atom should have a alpha hydrogen. So this should be attached to any hydrogen atom. If it is doing so, then this means that, sorry, this will be 1. I always write this as a 3 because We do that in the keto form. Okay, so this is oxygen now, which has a hydrogen. Now this is my position number 1. So again, from position number 1 I can shift my hydrogen to position number 3, and the double bond is going to shift between 1 and 2, exactly what we did for the keto form as well, right? Just you have just reversed the numbering to get the keto form from the enol form. We will be doing it for the other structures also. Then you will be able to see a enol and convert it into a keto form also in any difficult structures also that are given to you. Fine. Now let us see the next structure. So the next structure is an acetone. Again, let us identify 1, 2 and 3. My double bond and oxygen, this is my atom number 3, this is my atom number 2. Now on either side of this atom I have an carbon which has alpha hydrogen. This can be my 1, this can be my 1. So the total number of alpha hydrogens that I have for this structure is 6. This is clear. So I can make a enol in either of the two ways, this way also and this way also. Okay, and therefore you can understand that this is going to show tautomerism. So what will be the structure? Let us draw that structure also. So we have a carbon atom number 2. We have our atom number 3, which is also carbon, and 1, and this is my atom number 3 as it was in the keto form. So here it was a CH3. Now we will be putting a CH2. This was a double bonded oxygen, shifted of hydrogen from 1 to 3, so OH, and the double bond now between 1 and 2. So this is the keto form, the enol form, right? So you can do it the other way also. The structure you will be getting the same, because then the numbering you will be starting from the end where is the double bond. So again, so now can we make a keto form out of this? So what are we going to do? This is going to remain my carbon number 2, atom number 2, sorry. Then where we have a double bond, this is my atom number 3, and where I have a oxygen now, this is my atom number 1, because I can see a hydrogen with it. So again, from position number 1 to 3 we are going to shift the hydrogen and the double bond between 1, right? So again, what you will be getting is the keto from the enol form, right? I hope now you are understanding what we are going to do. Let me just clean it up. So this is what you are going to do for a conversion of a enol into a keto and a keto into an enol, right? So now let us quickly do the rest of the structures. So the third we have, again let us do the numbering. So this is my number 2, where I can see the double bond. This is my number 3, and now this can be my number 1 and this can be my number 1, because both of them, they are alpha carbons. Now alpha carbon, here this is attached to 1 hydrogen, here it is attached to 3 hydrogens. So the total number of hydrogens, the alpha hydrogen that I have, is 4 alpha hydrogens. And because now this is a unsymmetrical ketone, I can draw 2 enols for the structure. But the first of all, tautomerism is going to be present. This is what is clear from drawing that 1, 2, 3. Right? So now what are the enols that we can form? So one is that if you remove this hydrogen and shift it to this position, so what you will be getting is a carbon, a carbon, a double bond, a carbon, a OH, right, a CH3, and this was the position where we had a CH3, right? So this is one structure where we will be drawing, and the other structure which we can draw is a carbon, a carbon, a CH3, right? This is my atom number 2 now, and this is my OH, and now the hydrogen has been removed from this carbon number 1. Right, so this will be my CH2. So these are the 2 enols which are possible for an unsymmetrical ketone. Okay, either side you can remove a hydrogen if an alpha hydrogen is present. Now both of these, they will be formed in this case from the keto form, but one of them is going to be more stable than the other. The one which is going to be more stable is that one which is a more substituted alkene. This is something that you will understand more when you will understand all the mechanisms of reactions, which is going to be GOC part 3. But just remember over here that the alkene which is more substituted means it is having less number of alpha hydrogens, and there are more carbons attached to it. So as you can see over here, this carbon, that is, it is more easy for you to see. So this is a carbon which is having one alpha hydrogen, and this is the carbon which is having three alpha hydrogen. So this carbon is more substituted, more hydrogens being replaced by alkyl groups. So this is more substituted. So the alkene this will be forming is going to be a more substituted alkene, and this will be more stable. Okay, so the structure that will be more in the enol is going to be this one rather than this one. Okay, I hope this is clear. We will be talking more about it in the next lecture as well. So I hope you are getting things. Certain things, they will become much more clear when you have studied in detail about all the reaction mechanisms, what all is happening in those reactions. So then the things, they will become clear, and I would suggest you back to watch this lectures, the 2 lectures on tautomerism again. You will understand the concept better. Alright, so now it is just important that you understand what are tautomers and how we are going to convert one tautomer into another. That is more than sufficient if you learn at this position. And then after we have completed GOC part 3, do watch these lectures once again for having a better understanding. Right, so the next structure, this is formaldehyde. So here what we can see, identify, this is the double bond. So this is my oxygen, this will be 3, this is 2, and now this is 1. Now what I told you at one position was that atom should be attached to a hydrogen, but it should not be a hydrogen itself, right? But here what we have on both sides is only a hydrogen. This is not an alpha hydrogen. An alpha hydrogen is going to be one which is going to be attached to some atom which is next to the functional group. Okay, so this is not a alpha hydrogen. Alpha hydrogen would have been, then we had it carbon, next carbon is alpha carbon, so the hydrogen attached to it is a alpha hydrogen. So here we do not have any carbons attached to the functional group, so we are not having any alpha hydrogen. So this is going to be what? This is going to be no tautomerism. No alpha hydrogen atoms and no tautomerism. Clear? Perfectly fine. So you need oxygen, you need a double bonded oxygen to any atom, and then you need alpha hydrogens for tautomerism. So next is structure number 5. So in this structure, what you can see is this is a benzaldehyde. All right. So in benzaldehyde, now this is C6H5. The hydrogen from this is removed. So this compound, this is the carbon. So this is 3, this is 2, and this is 1. And this carbon does not have any alpha hydrogen again. So if it does not have any alpha hydrogen, then this means that it will not show any tautomerism. On the other side also, what do we have? Only a hydrogen, right? So this side also we have no alpha hydrogen. This side also we do not have any alpha hydrogen. So the next structure, this is acetophenone, and then this what you can see now, let us see. So this is my 3, this is my 2, this is my 1, and this can be my 1. So here you can see that we have 3 alpha hydrogens. This carbon again will not be having any alpha hydrogen. So the total number of alpha hydrogens, they are 3 alpha hydrogen, and therefore this compound is going to show tautomerism, but the tautomerism is going to be on the methyl end. Okay, so what you will be formed, can you draw that, or do you want me to draw it again? So this is going to be a pH. I am just drawing a pH. Okay, so this is my carbon, this is my double bond CH2, hydrogen shifted to atom 3, this is my oxygen with the OH. Right, I hope now this is clear. You are getting everything, you are drawing it, and you are getting the things correct also. So next structure, this is benzophenone. So we have a phenyl group on either end. So obviously this means that there are going to be no alpha hydrogens to the carbon. So no alpha hydrogen means no tautomerism. The next structure, again what you can see, this is a phenyl ring, a phenyl ring. So these will not be having alpha hydrogens, but in the center we have a CH2. So this is a alpha carbon which is having 2 alpha hydrogens. So 2 alpha hydrogens, this structure can again show tautomerism, and the tautomerism can be this one showing a tautomerism or this one, and this is a very important structure. We will be discussing more about it in the next lecture. All right, Next, so here what are you going to do? We have again number 1 carbon, sorry, number 2. This is number 3, and this can be number 1 and this can be number 1. Both of these two will be having 2 hydrogens each. So this will be a hydrogen, here it will be a CH2 groups, right? So this is also a CH2. So we will be having in total 4 alpha hydrogens. So this structure can also show tautomerism. It can be on this end, it can be on this end. Okay, so I hope this is clear. Do I have to draw it again? All right, let us do that, don't worry. Fine. So this is the ring. I think it is easy now for you people. You have to draw OH over here. You have a double bond over here. So this is the structure which is going to be the tautomer. The next structure, this is already, you have already seen and we have already discussed this also, that when you are going to draw a tautomer of this does have a alpha hydrogen, but you will be getting 2 double bonds together, and whenever you are having 2 double bonds together, or if the alpha hydrogen atom, you can say this is attached to a sp2 carbon, it will not take part in tautomerism, because then you will be getting 2 double bonds, and 2 double bonds together, they are going to be unstable, right? So I hope now this discussion is quite interesting. You have learned quite a lot, and you are going to learn quite a lot in the next lecture as well. So that brings me to the end of this discussion, but we are still left with discussion on tautomerism that we will be continuing in the next lecture, right? And as far as your doubts are concerned, mail them us at h2ochemistry@gmail.com, or you can put that in the comment section. You can also join us on the Facebook page of the channel, right? And the Facebook page that will be having the name as H2O, or it is going to be a group that we have made for the discussion for students, and that is H2O, the A to Z of chemistry. You can join any of the two, so that you can put your doubts, have healthy discussions with us, and prepare the very best. So see you again. Have a nice day. God bless you.